We can get started a little bit and talk about it. We're going to talk about robotics and some of it, the Marshall High School robotics team. And introduce myself right off, John DeKramer, one of the mentors. And Mike, let you introduce yourself.
Yeah, I'm Mike Braithwaite. I'm a shop teacher up at the school, and I'll be helping them out, mentoring the kids, helping them out and stuff here as well too.
So great. And
I'm Reed. I'm a senior at the high school, and this is my 4th year of robotics.
I'm Carter, younger brother. This is my 2nd year.
so, and kind of get in a little bit. We'll talk about robotics a little bit. First of all, we've got a few robots actually up here, and really what it comes down to when you look at it, you know, when you get a robot, size doesn't matter because they're all doing essentially the same thing. And well, they do what they're intended to do. They're designed to and built to accomplish a task. And a lot of times that task is what dictates what the size of the robot's going to be. In this case, it's a small robot, but it does a lot of what the bigger one, actually right now the bigger one, it's kind of seen its season and plus, so it's, if you notice there's a few things hanging off on it and a few things broken, it's gone through, well, we'll see some of the competition, what it looked like working, but yeah, they do take a beating. But a robot is designed to do a particular task, and sometimes that may make it a very small robot, it may make it a very large robot. This is one that if somebody's interested in it, it's fairly easy to work with and start learning how to code and how to tell it what to do. In this case, this one's instructed to follow a line, which unfortunately I don't have a line here, but would follow like a white line, and it follow it along and just keep going over and over. And that's what the instruction is. And you can play with it and change the instructions and have it do other things. So what, so really it, like I said, it accomplishes what it needs to, but there's a way that we have to talk to it. Basically, we have to let it know what to do. And the way that's handled is really working with a computer. And computers can be most any size. This is actually got a computer inside here. So this is, many of you are familiar with the term Arduino. This is an Arduino. It's a very inexpensive piece of electronics, and it gets you started in how to program and how to work with it and get it to do a lot of things. So this is actually how I got started into it, learning to program. Right now, I say they're inexpensive. You can buy these for about 10 bucks. You can download the program for free, and you can start learning how to work with it, but mostly on this one it's blinking lights. And then from there you can get up to doing a few more things. Actually the same computer that's in here is what's in this guy. And it programs the same way, just a lot more of the language, you might say bigger vocabulary. And a longer story of what to do, and it goes through the sequence of how to work with it. And that's how the programmers, guiders do that. And a programmer will work in conjunction with somebody that's doing the equipment or the hardware. And between the two, we'll figure out how to get things going. I've got another guy over here. You know, it's this guy hiding back in here. Had to kind of go where there's plugins. And this is Fritz. And Fritz actually uses, again, basically the same computer, same idea, and he can make them change positions. He's not, I don't have him fully operational, but you can see he's kind of intended to duplicate a human face and do expressions. He's got eyebrows that move. His eyelids are supposed to be opening and closing, but they need a little work on it, which does happen with robots. They tend to break and they need to get fixed, and they want some attention just like people. They need to have somebody spend some time with them. But this idea, and if you get a chance to, you can come up and take a look at it. It's actually operated by quite a few motors in here. I see actually 7 motors right on the top and a few more underneath. And the motors are intended to move each portion of it, whether it's the mouth or the eyes or the eyebrows or whatever. And by what we give a command on the computer or through the program tells it what to do. And as we progress through, there's different ways of doing things and working with it. There's like I said, there's small computers, large computers, or small robots, large robots. There's not a lot of difference basically on them. They all have some type of power supply. In this case, this guy just runs off of AA batteries. This guy, Mike, you want to pick up one of the batteries back there? Runs off of a 12-volt battery. Come on in. All right. Okay. Fun weather, so we're just getting going. So they've got a lot of things in common. They've got power supply, like I said, the batteries. Usually a lot of them are electronic, but they don't have to be electronic. They can be powered by a gas engine or something like that, and then some control system along with that. If they're intended to move, which most of them are, there's some type of power train. Either a series, in this case, there's 2 motors on each side, so we can, when this thing's operating, it would drive back and forth. A couple of reasons we're not operating tonight is kind of like having people around here, and it's pretty easy to run into somebody, and you can tell it doesn't have its bumpers on right now, and it probably hurt. That we don't want to mess up the room too bad. They've been known to go through walls. So try not to do things like that. But this one is, it's got motors on the bottom, and we can tip it over, and you can see actually it's got several motors on the bottom because of another task this one had to do. You can see the motor drive on each side, and we got a section here. So this one drives kind of like a tank. You might say it tracks one way, and then the other way, both wheels are all 6 wheels are running in the same direction. It'll go forward. If one's forward and one's reverse, it'll make a turn. So you can steer it around and move it back and forth. You'll see another set of drive wheels underneath here, and that's actually was one of the tasks that this robot was supposed to do, and we'll see that in a little while on the screen. It was intended to come up to a 19-inch step and pick itself up and drive up on the step. So we had a series of lifts, which I blocked them so they don't all fall out, and then motors on it so it could pick itself up and drive forward and drive up on a 19-inch step and park itself. That was part of the task at the end of the contest. So we've got, again, a power source, batteries, and that's in all of them. In this case, I said this was a little computer. Well, the power source is actually the computer here running. And it's got a motor drive. One of the other things it has in a number of different areas, and you don't usually see them all the time, is a variety of sensors. And for me, when I get into it, that's kind of the fun part for me, because I'm more in the electronics area, and now that Mike's on board, Mike can handle all of most of the mechanical, hopefully. But we do is we've got a camera, so it can actually the camera would sit this way, and you could see what's going on. The operator could see what's going on, and you can actually program the robot to recognize some things and say, okay, that's a particular shiny circle that I want to drive to, and it will drive to that. It's got switches that, in this case, it was picking up a disc, and we wanted to know that, yes, it had the disc, so close the switch when there. So that was a sensor. The sensors over here that would show how far, in this case, this is a distance one, how far away. And now this is intended to be a little interactive, so don't feel free to come on up here and take a look at some of the stuff. Some of it, you've got to kind of look at it to see. But we have a couple of ways of measuring distance. You see this guy is, actually it's a sonar unit. It's sending out sound waves, and it's bouncing. If it hits something, it bounces back and tells you how far it is. In this case, it's looking out 4,000 millimeters, which would be, quite a ways out here. And it sees, it's telling me that it's over 4,000 millimeters, so it's quite a ways out. And as it gets closer to something, or it sees something, then what you're missing here, looking at it, is got a digital readout telling how far away it is. Now that's just looking at it, but sometimes a lot of times the robot has to be able to do that on its own. So in this case, it's just rigged up that, okay, if it gets within, in this case, 100 millimeters, and then we can see the light when it comes on. I'll do it this way. When it gets close, it turns on a light, so it knows where it's at, and we can adjust that very easily by just changing the number within the program. And it may be 100, it may be 500, it may be 2,500, whatever we want it. So we know when we're driving a robot like this, and that was the purpose of this sensor that's on here, that we're driving a robot, you want it to get right up to a wall maybe, but you don't want to crash into the wall. So in this case, what it was doing is it was driving, it was counting down the distance, and when it got to a certain point, it would slow down, next point it would stop. And then if the driver needed to manually drive it in the rest of the way, they could. But we control part of it by sensing different directions and different things. Again, this one, built on this unit, was also similar to this, another line sensor. So it could follow a line, and so in this case, in order to pick up this disc or drop off the disc, it had a line that came out about 18 inches, and we could line up, we could drive up to it. It would pick up that line, and it could go up and drive right to the center and center itself up, just following that line. And again, it's another sensor like this, and I'm going to turn this way. So you can kind of see the same thing. As it sees nothing or dark, you just see a red light. And when it sees the line, you saw a green light, green light's on and green light's off. And by using at least a couple of these things, or maybe 2 or 3 of these, we could look down and say, okay, there's no line here, there's a line here, there's no line here. We're centered up on it. If we saw it on this one, were off to the side. So we had to steer the robot in a little bit until the center one is the only one that saw the line. And those are ways of doing this with sensors and guides. And that's part of the programming. And that's how you talk to the unit. And you tell it within the program, look for a line. When we push this button, look for a line and line yourself up on it and drive forward. And we could tell it that it drives so fast or how slow, or, you know, when you get to within a certain distance, you stop. And those are part of all the programmings that we work on. Now, there's all kinds of other sensors. We talked about the camera. Sometimes you want to follow something that's red or follow something that's green. So you could have a color detecting on it and work with it. We have also another sensor, this guy, which unfortunately bringing him over here broke a wire on, but so not both wheels don't work. But this guy's actually got a compass on the top, so it knows when it's aiming north and south, which are all 360 degrees, and it's got a GPS unit. So it knows within a range of where it's at. So what we can do, in this case, it has a location programmed in, and what it's designed to do, and unfortunately the other wheel isn't running, but it would turn itself slowly in a circle until it lines itself up on the compass and says, okay, that's the direction I'm supposed to be. Reading the GPS coordinates and the compass setting, it says, okay, I want to go, in this case, it's that direction where the target is. And if it gets off on it, it will stop and turn itself around again until it gets to that direction. It picks up that right compass reading again and takes off again. So it looks at both compass and GPS. And I think GPS in here, inside a building, it doesn't pick up a lot of signal, so I'm not getting the signal that says it's got a full GPS reading on it. So it might have a little more difficulty inside. And those are some of the things that we have to work with as we work with robots. What's the condition? Where is it going to be? How do we account for that and work with it? Where we're doing some of the, the indoors things with the competition in this one, a GPS may not work so great because we're inside a building all the time. Metal buildings, you can't always rely on getting enough signal through. But when you get them outside, and one of the reasons that, okay, you got a nice big long stick in here, because the compass reads a magnetic field. But you got to watch out because the motors operate off of the magnetic field. So in order to keep it away from the field, I moved it up towards the top, and then now I'm far enough away from the motors won't affect it. But that would drive going into the direction it wants, looking at the sensors. And again, these are not, for somebody that wants to work with it and start learning with it, these are not items that are very expensive. I mean, a lot of these things, this setup is, well, in total, everything is, less than $100. So, and that's adding on, that's the GPS, the compass, and the whole works. So, you can play around with these things for relatively inexpensive and start to learn how to talk to a robot and learn the programming. Now, when it gets to programming, that's another whole issue because machines work in their own, basically in their own machine language, which humans have a very difficult time understanding. So what we do is what's been created is a programming language that humans can understand. It may be confusing if you're first looking at it, but if you don't know French and you look at French, you say, I don't know what they're trying to say. Well, same thing for a robot. But what you can use is a programming language that then gets converted over to the robot itself. The program that we're using on this one is called Java. It's a type of programming language. The program that this uses is C++. They're very similar, but they have different commands. And just like we talk to each other, we need to be conscientious of our vocabulary, our punctuation, and just what words mean beyond the vocabulary. Robots and programming is much more defined. Commas are very important in certain areas. Semicolons are very important. Spelling, just like if you're writing a letter, spelling is important. Well, in computer language, for the computer to understand it, yeah, the spelling has to be correct, the punctuation has to be correct, the capitalization has to be correct. And so it's just like it is learning another language, although it's probably a lot slower vocabulary and a lot less structure than you might say learning an English language. So that's just different ways of talking about it. Let's get into a little bit of what these guys are about, and let you guys do some talking about it too. But Marshall High School has got a robotics team, and usually we get started trying to get organized a little bit around December, so we know a little bit what's going on, November, December, so start getting the group together. But the first weekend in January now, we'll be starting our 2020 competition season. And what occurs on the first Saturday in 2020 is the organization that we work with, First Robotics, will put out a very short video, about 2.5 minutes, or 2 minutes to 2.5 minutes. And from that, we determine what our task is. And as the team decides how they're going to build the robot, what kind of wheels are we going to use, how's it going to drive, what's it going to do, and it's got several tasks that they usually can do. Do we do all of them? Do we do one of them? That's all decided by the team. And go from there. What, let's see, keep turning them off, but I'll show you. Let's see, come back on. This past year, 2019, this is the video that they played. And unfortunately, I don't know, can we get more sound in here than that?
I'm not sure.
Each alliance has 2 rockets, 1 cargo ship, and a habitat. Hatch panels and cargo are available through the player stations, and cargo is also available in
I'm hoping they can get it coming through the
robots
speakers or
start in
something.
their habitat and may be preloaded with 1 K-piece. Alliances may also
See
choose
those lights
to
be
load
on.
some phase of the cargo ship with either hatch panels or cargo. During the first 15 seconds of each match, driver vision of the field will be blocked by a windy sandstorm. So robots must be controlled using either autonomous code or manually with a vision system on the robot. Alliances are points to maintain habitat, secure hatch panels, and any cargo that's properly stored. Cargo not secure spills from a cargo ship. As the sandstorm ends, driver vision returns, and alliances continue to earn points until the user is back. Alliances may rank over qualified matches for completing 1 rocket with patch panels and cargo. Near the end of the match, robots return to the safety of their habitat for the upcoming launch and earn more points. The alliance that earns the most points wins the match.
And I'll kind of go back through a little bit of what they did, and maybe we can just get a reset back to the start. Again, we start out in a environment of 3 teams against 3 teams. And those 3 teams are randomly shifted through all of our competitions. We ended up playing a total of 9 different competitions at the University of Minnesota. And so each time we had a different set of teams. I don't think we duplicated any of them.
Yeah, I don't think so.
So we had to take and put a hatch on the yellow circle. We had to take one of those, put it on the door so the ball wouldn't run through. The orange ball behind you there is the cargo they're talking about. Usually involves we have to try and pick up the ball if we want to. And in this case, it was pick it up and try to drop it through one of the circular holes or up on the top. So they were putting the hatch on and then putting the balls in. So that was the main part of the task. We tried to get as many of these done in the 2.5 minutes of the competition that there was. In this case, we spent a fair amount of time working on picking up a ball and picking up the hatch. And then we sat down as we were talking, more we talked about it, we decided that, you know, it's great to put the ball on, but you gotta have hatches on first, and we're gonna be working with other teams. If we're really good at putting the hatches on, we're gonna get more points that way than anything else. So we ended up removing our ball pickup, and because all of those items take up more power and you're limited on how long you can run and everything else, and we decided to strictly go for attaching hatches. We also decided not to go for the very top one. If we get the 3 heights that were shown in there, there's actually 3 different heights. If we could get to those and put on all those, we'd have to be very fast in the first place because there was like 18 hatches that you could put on. And it was, what, 2 points apiece?
Yeah.
And so we could actually chalk up some pretty good number of points. And then in the end, like we talked about, we're going to try and climb that big step in the center. So that was our plan, and that's what we went after. So the students design the robot. There's certain conditions we have to meet. There's certain physical sizes that you have to be. There's a certain weight that you cannot exceed. And that was part of our thing with we took off the ball pickup. That meant that it was less weight that we had to contend with. So I made our robot a little lighter and we could do a few other things with it. And went from there. Now, either Carter or Reed, you want to
Yeah.
talk a little bit about the
So right now,
competitions?
they're showing at the beginning of the game how we could set up the field, and then you'll see how the screen drops down. It was the sandstorm period, so we weren't allowed to see what's going on unless we had a camera. So we had a camera right here pointing down so we could see what's going on, and then we could have done that, or we could have had it all autonomous. So we could have had programmed to make the robot do everything by itself without controlling it. We figured that would be harder, so we put the camera on and controlled it with view from the camera. Sometimes the camera didn't work though, so it was going in blind, but that's what makes it fun. You never know what's gonna happen. So yeah, we had that for that. So if you, in the video, if you saw in the middle step, a robot climbed up, had 2 wheels pushed down, and they went up and then moved over. That's what our robot was supposed to do. with our wheels in the bottom. That didn't work so well because the robot's really heavy, and so that was difficult, but we did it once. We did, I think, one time.
One of the other things we talked about, I just wanted to point it out, is, you see it in the picture here, they had lines coming in right here up to where to put the hatch. So they're only just showing it on the one, but actually each one of those slots had a line to it. You can see a little bit over on the side picture there. So that's where the line following came in. You could come in close, and then you could line it up, and you could use either the camera, and we had it kind of targeted in the center, so we knew where to go, and or you could use the line following to put your robot right in the center, because it had this Velcro all around the ring, but it just has certain spots where the Velcro would attach to the wall. So that was how we got in and attached.
So, like he was saying with the line sensor, to pick up the hatches from the loading area, it was in this tight spot, so our robot just barely fit. It was like this wide. So if we wanted to get into it, we had to go straight in, and so that's what the line sensor really helped with. We would line it up, press the button, and it would just follow the line. It did it all by itself. All we had to do was press the button. It'd go up to the line, we'd put the panel right there, and then we'd lift it up, pick it up, and then we'd back out, turn around, and go and place it on top of it. So the line sensor was a big help. It was definitely worth figuring out the programming for that one. Let's see. What else?
I say, since we had two other team members, we were hoping we'd at least get paired with somebody that could put balls in, and that actually worked out pretty well. There's just to kind of give you an idea, the competition that we went to, called 10,000 Lakes competition, University of Minnesota, is actually one of 3 that are in Minnesota that go on during the season. We had 66 teams at that one. At the same time, there's another group going on that North Star, that's another 60-some teams. There was a group that were at Duluth. Actually, there was one in Duluth, and there's one in Superior, Wisconsin, both going on at the same time. And each one of those had in the area of about 60-some teams at it. So there actually turns out to be more robotics teams, high school robotics teams in Minnesota than there are hockey teams. So for those that are, really into hockey, yeah, we got you beat. We got more robotics teams going than we got hockey teams in Minnesota. So,
Do you have any videos of our competitions?
yeah, actually we had you and I don't drive this. Was it my pocket? You are in,
Try to find something.
actually you can, I think just that first one, it's not us, but it's the Pups of the Week. Let's see what.
I think this is just epic. This is
Or you
one-
can do qualification 17, San Francisco Regional, just.
Here's an idea of,
Get an idea of what this competition looked like. And say, we did this 9 times at the University of Minnesota. You start out with all kinds of balls out in the area. And in this case, it is, okay, that was the end of the autonomous area. So that was the time when the robots either were working on their own or with the vision system. And now the team members are on each side, 3 teams on each side, attaching the hatches and coming in and putting the balls in. And in some cases, you'll see attempting to put balls in.
So if you see this one over here with the red bumpers, it's got blue and black machining, how it reaches up really high. That happened to be one of the teams that we went against, and they're in San Francisco right now in this one. And they came to, I don't know where they're
Colorado.
from, but they go all over. They're really good team. They always win a lot.
So how did you guys do in your competition?
What was it?
We were pretty much in the center, might say the center of the pack. I think we were in the high 30s, I think
I
38.
think this year we did pretty good.
Yeah.
We had 36.
And it does depend a lot on the fact that you're actually working with 3 teams. So you pick up the score if you've got 2 good ones with you, you're great. If they have some troubles, which at times we've had troubles too. We had, something gets hit wrong, power goes out, robot stops, the robot resets, and you're shut down for a while. It happens, and these robots fall over. They get knocked over. I've only seen it on one occasion where we were at a competition where a robot fell over and one of his team members actually came over and picked him up and set him back up so they could get playing again. That's a little unusual that you can actually do that. Now like here, there's one in the center. He actually wasn't the one climbing, but he set himself up on a ramp so they could hopefully climb up. But as you can see, that's a pretty steep ramp. And it's hard for, especially wheels like these, it's hard for those tires to grip in and climb that. So we had a few robots that did that and said, well, rather than us climb, we'll assist our teammates in climbing and get the points. But there are certain sizes that you have to stay within when you're operating. And so that made that ramp very steep. We actually looked at that, and then we tried climbing that. We set up a ramp and tried to climb that and see how it goes. And we said, yeah, we can't do it with our wheels. We're not going to rely on somebody having wheels that are better than ours to be able to climb that. So we gave up on that idea and decided to just try and go for it ourselves and climb. Here's 10,000 Lakes. No. But this is up at University of Minnesota. And we got a nice ad inside there. Okay. Actually, we were at 92. We're at 92, so if we could find 92. I think we were in that one. And like I say, you can see, oh, okay. Yeah, let's try that one. I'm pretty sure we were in that one.
I'm 90 something. Yep, there we are.
2515,
There's
8,
our number right here.
or,
We're back left, or far right, I guess, on the.
Yep, up there on the top right, we can see us trying to pick up a hatch panel.
yeah. And now there's during the competition, they could have, the opposing team could have one robot downfield running interference, trying to mess with you, which is pretty easy to do. And getting kicked around. Now they also have refs that, you can't block somebody, but you can stall them for a few seconds. Ah, there's one that just went over, the blue one that just tipped over on the back. And we tried to climb that big step and didn't work.
So it's not real easy to see, but I'm the one controlling the robot on this red side, on the far side of the pickup.
I was
We control it with our computer and our joystick. So we have our turns and buttons and whatnot.
During this time, we had actually 2 controllers. I was controlling the lift because our lift basically would go into the ring and then go up to catch it in that little hook. And I was the one controlling that, so there's more than one driver usually helping out.
And you're only allowed a certain number of students back in there, plus one mentor, and setting up and running. You can see it was down to, okay, it was 2 seconds left. Okay. Yeah, we ended up winning that one, 38-52, I believe, so, nice and short. But, and that's how you get ranked out of there, because all 3 teams then use that 52 and that ranking to position them. And you can see we had, oh, you kind of make out some of the things. We had several of the vertical rockets going, and that's a little animation in the end saying that the red team won. You see there's always our red team against the blue team working on it, so.
It's definitely a lot of fun. So when you're in high school, if you're at all interested in anything, programming, building, anything.
Mechanical, we have graphics that we use. What we haven't done too much in the past and would like to be able to do if somebody's interested is do a website and put some things out, promote ourselves out on the website. You know, the graphics that we use, these were done by students. This was 2 years old, but students did that, put it together. In this case, we ordered the t-shirts and sold the t-shirts. We're wanting to get that. We've had students up there that were in the Tiger mascot so that we can promote ourselves. One thing that happens at the end of the competition, you do these 9 sets of competitions and you get ranked. The top 8 teams are the teams that definitely get into the finals. Those 8 then pick 2 other team members to be with during the entire finals. So even though you are not in the top, even the top 16, the top 10, as long as you're below number 8, any point in there, you may or may not end up in the finals. If somebody says, hey, that team really complimented what we did, they could do things that we could not do, they would choose that to work with them and be part of their alliance for the rest of the quarterfinals and the finals. And that's partly what you want to do is promote yourself that, hey, this is what we can do, this is what we're capable of, this is what the robot is doing. You know, how good are our drivers, all the operators, how are we doing all these things? And then trying to work to get yourself, if you can, into the finals. But one of the things that we do tell the students all the way through is really, if you made it to the competition with a robot that's performing, you know, you've already won. Because you're accomplishing your task. You set out to build something that didn't exist. You had, other than the physical size and the weights, physical size, you just have to be, it's actually under 10 feet around, 120 inches. You can be any shape you want, any type of drive system you want, as long as you're using no more than, in this case, 6 of these motors. And you have to use the same battery. And those are kind of the conditions. Beyond that, the students have, within reason, whatever they want to do with it. So we have that mechanism that we had to lift it up was actually air cylinders. So we had an air compressor. This thing moved in and out with air and a few other things. So quite a few different aspects that you get to work on. So I think I'm going to stop at this point and ask if anybody has any questions, would like to see something or find out about something.
Well, I wondered, I was thinking about, you know, we were talking about earlier with the one with the GPS, you know, it would be kind of cool for a project to try to make a driverless car just for the high school, you know.
Yeah.
You know, you can only do that with the white sensor and the white line sensor and
Absolutely, because you can do things like, you know, just, okay, you can't go any closer than a foot away from a wall, and so you're looking for that spacing on a wall. If you can have a white line or between the white lines or the GPS setup, I mean, there's all kinds of things that you can do. And yes, that's, you know, teams that are out there that basically run all year round, that's the kind of projects they take on. You know, there's a lot of things you can have fun with on a robot doing. Like one place in Marshall here that's made a robotic snowblower, which might come in handy here real soon. Yeah, there's a number of other things that can be done, and yeah, it's just a matter of, hey, what can we do? How can we put it together and work on it? And it's a combination, again, of the mechanical, how do we get this thing to work? You want to run fast, you need power and slow, you know, whatever the limitations are or not, then you know, you can work with it. But yeah, any kind of task like that, it's kind of fun to just stop and think about it and say, okay, what could we do? And well, do it. What about you guys? Any questions?